is equal to 1. I think this is okay. I don't remember what the constant is, but you need to prove something like that. Okay, and then you use inverse Fourier transform. Okay, I will modify it and send it to you this afternoon. And I think if you have that, actually, you don't need to in the exercise, to assume the other thing about the integral of 1 minus cos. Okay, so yes, today I'm going to finally talk about strong disorder. And in fact, I'm doing... Okay, so remember the definition of strong disorder. Okay, we have the partition function of our model, which is the expectation with respect to the simple random walk of the exponential of beta omega n x n minus lambda beta. Yes. If Wn beta omega tends to 0, P almost surely, we say that we have strong disorder. Okay. So I just told you that we were going to explore the properties of the polymer in the strong disorder regime, but this is not exactly what we are going to do yet. Now we are going to look at a stronger notion of strong disorder, which is very strong disorder. Okay, so for this, I need to introduce something which is kind of well, something common in to all statistical mechanics model, which is the free energy of the model. Okay, so we'll introduce a definition. The free energy of the directed polymer is defined by f beta, which is the limit when n goes to infinity of 1 over n times the expectation of log Wn beta omega. Okay, so okay, let me perhaps give you a little bit of context. So first, well, this thing is a misnomer because, okay, in a sense, a free energy, it should be something, physically it should be something which is, in terms of dimension, it should be homogeneous to an energy, okay? So what's the energy? The energy is h, okay? So you have exponential beta h. So beta, I call it the inverse temperature, but in fact there is Boltzmann's constant playing a role there. So beta is really such that beta h is dimensionless, okay, so that you can take the exponential. If you want to take exponential or logs, you need things to be dimensionless, because if not... so yes, I mean, like this partition function is dimensionless, the log is dimensionless. Here you have something which is dimensionless. Yeah, truly physically speaking, the free energy should be 1 over beta this. Okay, so this is sometimes referred to as the pressure in the physics literature. The other thing is, okay, free energy, in fact, it's really 1 over beta times the log of the partition function. Here, what we are looking at is, well, the asymptotic free energy per unit of volume. Okay, and the expectation here is just so that it converges, okay, or so that we have an easy proof for the convergence. But you will see in a second that this thing also converges almost surely to F beta. Okay, so F beta, it's something that controls the exponential growth of Wn. Okay, here you know that Wn, it has expectation 1, so it cannot grow. So what I mean by exponential growth is exponential decay, and this thing will be non-negative. Okay, so perhaps. Note. Which is equal to 0. Okay, this is good. So F beta is. Okay. So let me first prove you that this limit exists. So proof of existence of F beta. Okay, so what we are going to show is that the expected log partition function is super additive. Okay, so recall I'm going to use mu n. Well, it's just the endpoint distribution of my polymer. So it's just p and beta. Okay, well, okay. Xn equal x. Okay, remember this is a point-to-point partition function. Okay, the partition function limited to trajectories, restricted to trajectories that end up at x. Okay, so remember that we have so let us prove this, okay? And then from this, it's easy to conclude that F beta has a limit. We'll do it later. Okay, so Wn plus m, we have already shown that this is equal to the sum for x in ZD, W and x, theta and x, W and. Okay, and you can rewrite this as Wn times the sum over x in ZD, mu n x, theta and x, Wn. Okay, so yes, you have automatically that the expectation of the log of Wn plus m, well, it's equal to the expectation of the log of Wn plus the expectation of the log of sum of mu n x, theta n x, Wn. Okay, remember, theta and x, it's a shift operator on the environment. Okay, I'm just looking at the partition function, but the starting point, instead of being 0, 0, okay, it's nx. Okay, and now I'm going to look at this term here, and I'm going to show that this term is larger than log Wm. And the reason is simply because, well, it's a linear combination of variables that are distributed like Wm, so I can just use this thing is a linear combination, convex combination of variables that are distributed like Wm, so I can just use the Jensen's inequality. Okay, so let me write this. So if I look at the expectation of log of sum of x in ZD, mu n x, theta n x, Wm, well, if I look at it condition to Fn, okay, basically I want to consider these things as constants. Okay, so I'm just conditioning to. Then, okay, I can use conditional Jensen, okay, for mu n. And I get that this is larger than sum of, okay, so sum over x in ZD, mu n x, log theta n x Wm. Okay, now this is Fn measurable, so I can take this out. Okay, and now this is independent of Fn and distributed like Wm. So this is larger than this. Okay, and then you get that 2 is larger than this just by taking the expectation here. And yeah, this kind of thing is exactly the type of thing you try to prove when you try to prove free energy. It's valid in one dimension. It's also valid in dimension more than one when you try to patch things in. Okay, here I mean our model is one-dimensional in the sense that the object, the graph of the works, it's a one-dimensional object. Okay, it lives in a d plus one-dimensional space, but it's a one-dimensional object. You have models in which basically the volume of the system is n to the d. The state space grows exponentially in n to the d. And in that case, okay, you need a different version of superadditivity. But this is basically the kind of things you try to prove. And sometimes you need to have correction terms for things to be true. Okay, and then you need to work a little bit more. Okay, so let's see how we can conclude once we have superadditivity. So I guess this is something that some of you may know. It's called Feket's lemma. And it tells you that if an is a sequence such that A0 is equal to 0, and for all n m larger than 0, an plus m is larger than an plus am, then the limit when n goes to infinity of an over n is equal to the supremum of an over n. Okay, so the supremum over all n. And I think you need the supremum for n larger than 1 here. Yes. Yes, of course, because you're dividing by n. Okay. Okay, and yeah, so I think okay, traditionally the lemma might be stated for sub-additive sequence, but this is exactly the same thing. Okay, so yeah, the proof is well, okay, not super complicated. What you want to do, okay, first you just need to show that the limit of an over n is larger than the sup an over n. Okay? Okay, I will focus, I will assume that this sup is finite, which is fine for what we want to do, because yeah, we are the limit cannot be positive. So, yeah, somehow the proof works exactly the same way if the sup is infinite. So, yeah, what we are going to do is to fix m epsilon. Okay, so let's say the sup of an over n. I call it L. Okay. And I fix m, which is m of epsilon, such that an over n is larger than L minus epsilon. Okay, so if it goes to infinity, if this is equal to infinity, here I would just put a large constant. Okay. Yeah. Now, for n large, what I'm going to do is I'm going to consider the Euclidean division of n by m. So this is equal to mp plus q, where q belongs to 0, m minus 1. Okay, so what I have is that if I look at an, okay, well, it's equal to an minus m plus m. So I can always say that this is larger than an minus m plus an. Okay, and I can repeat this thing as long as this thing is larger than m. Okay, so I get this is larger than an minus 2m plus 2am. Okay, just taking an am out of this. And in the end, okay, or at the beginning if n is small, but you get that this is larger than aq plus p times am. Okay, and perhaps, I mean, these things should be called Pn and Qn. Okay, so now AQN, it is larger than the infimum over I in 0 m minus 1 of AI. Okay, so let's just call that, I don't know, alpha. Okay, so what I have is that AN is larger than alpha plus PN AM. So in the end, I get this. Okay, and now I can take the limit. So taking the limit, I get that, well, the lim inf of an over n, it's larger, well, than, okay, everything converges here. So it's larger than the sum of the limits. Alpha over n goes to 0. Am, well, it's a constant. Okay, m is fixed. Pn over n, it goes to 1 over n. Okay, because Pn is the quotient of n by m. Okay, so plus Am over m, which is larger than L minus epsilon, and we're done. Okay, so now the other thing I want to prove to you is that yes, you don't actually need the expectation to have convergence, and for this, what I need to show is that log Wn is actually very close to its expectation. Okay, so I'm going to prove this under the assumption that the environment is bounded. Okay, I've taken this assumption at the beginning, but most of the time I haven't used it. This is one of the places where you use it. Well, somehow it's not needed, but I think it's better to have this assumption here because it gives me the occasion to introduce you to a general result that might be useful for you in other contexts. Okay, so proposition. So it's called concentration of log Wn around its mean. Okay. So assume that the expectation of W1, 0, the probability that this is larger than m is equal to 0 for some m larger than 0. Okay, then what we have is that the probability that log Wn minus the expectation of log Wn, the probability that this is larger than u, this is smaller than exponential minus, okay, so I think here what we have is beta m square. Okay, I will have to correct this if this is not okay. 2 beta m square u square divided by n. Okay, so and with a 2 here. Okay, so what it means here is that basically, typically, the difference between this cannot be more than square root of n. Okay, as soon as you take u significantly larger than square root of n, this thing starts to be crazy small. Okay, so this is a concentration result on the scale square root of n. Okay, and this is just one bound. Actually, it's not expected to be sharp. Somehow, well, you see that. Okay, when you are in weak disorder, okay, well, we have not proved that, but this should be typically finite. And this is typically finite. I mean, the distance is typically 1. Okay? But somehow the good thing is that it's a rather robust result, and it's valid throughout all the phase diagram for every u, and the constants are even explicit. Okay, so a consequence of this is that, well, the probability that log Wn minus E log Wn. Okay, let's say the probability that this is larger than n to the 3/4. Okay, well, this is smaller than 2 exponential minus c beta n to the 1/2. Okay, so this is really small. In particular, this thing here is summable. Okay, so that you have that the limit when n goes to infinity of 1 over n. Okay, let me write it like this. Minus f beta. So this converges to f beta. Okay, just because, yeah, this thing, you know that it's smaller than n to the minus 1/4 for n large. Any question on the result? Okay, so I will comment a little bit on this result and then introduce, you know, this notion of very strong disorder that I promised you at the beginning of the lecture. Yes, let's first prove this, and to prove this we need to do some detour and to talk about a general concentration inequality for martingale sequences. this is called Azuma-Hoeffding inequality. So I don't know exactly what the story of this result, but I think Azuma is really the result concerning martingale, and that Hoeffding's version is for sum of IID random variable, sum of independent random variables. Okay, so we are going to consider a martingale, okay, which is indexed by integers from 0 to big N. Okay, I mean you may want okay, you may have the and you can complete it into a martingale index by the whole integers just by taking it stationary after N afterwards if you want, but okay, so just a finite martingale sequence. Okay, well, a martingale sequence with finitely many steps. Okay, and I let f n equals 0 to n to be the associated filtration. And I assume that M0 is equal to 0, and that for all n in 1n, mn minus m n minus 1 is smaller than k, where k is larger than 0. Okay, so I'm just taking this assumption to make the proof simpler to write. If you want the best result possible, you may assume different bounds depending on the value of n, and you might also have the upper bound and the lower bound differ. Okay, but for us, we don't really care about the constant that you have in front of the u square, so this will be good enough. Okay, and then the conclusion is that mn is larger. The probability that mn is larger than u is smaller than 2 exponential minus u square over 2n. Yes, of course, yes. Square. Yeah, yes. Yes. 2 u square over n beta n square. Yeah, okay, it's kind of obvious that like the concentration should get worse when beta increases, and okay, at least it should get worse when m increases, because your assumption is increasing. Okay. Okay, so let's prove this, and then we are going to apply it there, where you have no martingale, but you will find out that there are martingales everywhere, in fact. So, and then we will move on. Okay, so how do you prove this? Well, okay, so first, you only need everything in our assumption is symmetric, so you only need to prove that the probability that mn is larger than u is smaller than 2 exponential minus u square over 2 nk square. Yes. And there is no 2 here. Okay? Just because the probability is that mn is smaller than minus u, it's a probability that minus mn is larger than u, and minus mn satisfies exactly the same assumptions. Okay? Okay. So now the idea is to prove this, we are going to prove to control the Laplace transform. Okay, so what we have is that the probability that mn is larger than u, well, this thing, it is smaller, well, it's equal to the probability that exponential lambda mn is larger than exponential lambda u. Okay, and here I'm taking lambda positive. Okay, and so this is smaller than exponential, the Laplace transform of lambda mn times exponential minus lambda u. Okay, so what we are going to prove, okay, so we need to prove that this is smaller. Okay, I'm going to prove things by induction. So we are going to prove that this is smaller than exponential and lambda square k square over 2. Okay, for all n in 1 n. And we are going to use that over here. Okay, so what we have is that the log, okay, of the probability that mn is larger than u, well, it's smaller. Okay, and here, what I can do is, okay, okay, it's smaller than, okay, the log of that. So the log of that, it's n lambda square k square over 2 minus lambda u. But I can take the infimum over lambda positive. Okay, yeah. It's valid for all lambda. So I'm just replacing this by this bound and taking the log. Okay, and this is it, because now if I want to take the infimum, well, I just need to take the derivative. So yeah, I get that this is minimized when lambda times n k square is equal to u. So lambda equal to u over n k square. Okay, and then this is equal to u square over 2 n k square, which is what I wanted with a minus. Okay, you get u square over 2 n k square minus u square over n k square. Okay, so we are going to prove this, and I'm going to start with the case. I'm going to start with the case n equal 1. Any questions so far? So this is called Hoeffding's lemma. Okay, and this is if x is smaller than k, and the expectation of x is equal to 0, then the expectation of lambda x is smaller than expectation. Yes. This. Okay, so what's the key here? So the key about this lemma is really, yeah, just, okay. Here, the important thing, okay, perhaps there is a lambda square missing, right? Yes. Yes. So really the key to make concentration work or anything is you want this thing to grow like 1 plus gamma square time lambda square times the constant. Okay, and this is relatively easy because here, okay, if you use Taylor, basically, yeah, the first term is problematic, but the first term has expectation 0. So really, there is just a little trick to get optimal constants here. Okay, this is the only thing. So proof, yeah, the idea is to say, okay, instead of just subtracting the linear part, what I'm doing is I'm saying, okay, x, I can write it as a convex combination of k and minus k. Okay, just because of this. Okay, so x is equal to alpha x k plus 1 minus alpha x minus k. Okay, where alpha x is equal to x plus k over 2k. Okay, so in particular, the important thing is that the expectation of alpha x is equal to 1/2. Okay, now I'm using convexity. So I have that this thing, it's smaller than exponential k times alpha x plus 1 minus alpha x times exponential minus k. Okay, so taking expectation, I get that the expectation of exponential lambda x, well, this is smaller than the expectation of this, and the expectation of this is exactly hyperbolic cosine of k, of lambda k, and there is a lambda here, and there is a lambda here. And I am assuming that lambda is larger than 0 because, yeah, I can, well, first I only need the result for lambda equal larger than 0, but then my assumptions are symmetric. Okay, and this is smaller than expectation lambda k square over 2. Okay, well, to check that this is true, well, you can write the Taylor expansions of the two, and you see that the coefficient there, I think they are all smaller than the one that appears there. It's true for the two first coefficients. And clearly, it's also true asymptotically. So. Okay, so n equal 1 is done, and now we are going to work this by induction. And basically, when you work this by induction, what you are going to do in the induction step is use Hoeffding's lemma, but for the conditional expectation. Okay, so yes, what is lambda mn plus 1? Well, it's the expectation of exponential lambda mn plus 1 minus mn times expectation lambda mn. And now I can rewrite this as the expectation of, well, this thing. Okay, basically, okay, let me write it in two steps. This is the expectation of the conditional expectation, and now I can pull this out. Okay, so I have expectation of expectation lambda mn plus 1 minus mn. Okay, and now I think we're good because mn plus 1 minus mn is smaller than k, and expectation of mn plus 1 minus mn knowing fn is equal to 0. So, yeah. We are exactly in the setup to apply Hoeffding's lemma to the conditional expectation. Okay, and yeah, I mean, basically, it's not true that everything you prove for expectation is true for conditional expectation, but here you can see that the proof doesn't change if you use conditional expectation. So therefore, what you have is that the expectation of lambda mn plus 1 minus mn knowing fn minus 1, this thing is smaller than expectation lambda k square over 2, and then you use you replace this there, you use the induction hypothesis, and you get minus you get n plus 1 lambda k square over 2. Okay, so this is okay. So this is not very difficult to prove, but it's a very powerful result. So basically, this tells you that not only that if you have a martingale with bounded increments, you have concentration, but also if you have an assumption on the distribution of the increments, then you can get concentration results. So the way you would do that is to say, okay, with large probability, all my increments are smaller than some value k. That may depend on, I mean, you can tune it as you want, okay, so that this thing would be true. So imagine that your increments have exponential decay. Like they have exponential tail uniformly in n. Okay, so then if you take k equal, say, log n, you know that by a union bound, all of them will be smaller than a large constant times log n. Okay, and then you say, okay, so with large probability, my martingale corresponds to the sum of the truncated increments. Okay, I can modify them a little bit to make this a martingale. Then I use Hoeffding. So in the end, I mean, I will not get something as good as in the bounded case, but I can get concentration inequalities in that case. So therefore, in the polymer case, for instance, this is a way you can get concentration inequalities if you only assume that omega has exponential moments. And the fact that omega has a Laplace transform, it's a necessity for us to have this discussion about weak and strong disorder. So this is even not an assumption. Okay, so if you want to know more about this, you can refer to the paper of. Yeah. So what I'm telling you today, it's in a paper of Komets, Shiga, and Yoshida. I think it's published in 2003. Okay, and in particular, you have this. Concentration inequality, okay, without the assumption of boundedness. Okay. So now the question is, where is the martingale in when I'm considering log Wn? It's a fair question, and yeah, the idea is that. Where should I erase? Perhaps here. Okay, so the idea is that if you have a random variable and a filtration, automatically you have a martingale. Okay, so what are we going to do? Well, we are going to define, so given n, we set m n n equal 0 to n. Okay. Given n and n in 0 n. Okay. I set this. This is equal to, okay, the expectation of log Wn, knowing Fn. Okay, and here because I have assumed that m0 is equal to 0 in Azuma's inequality, so I have to delete this. Okay, where, remember here, Fn is just sigma, small sigma of omega n, kx, k smaller than n, and x in zd. Okay? So I'm considering a filtration, and I'm just considering, well, the sequence of conditional expectation with respect to that filtration. Automatically, okay, just because of the Tower property for the conditional expectation, this gives me a martingale. Okay, so the only thing I need to check is that the increments are bounded. So the property is that mn plus 1 minus mn, this is smaller than 2 beta m. Okay, and yes, let's take a small break, and I'm going to prove that just afterwards. Any question? Aqui a gente vai usar. Aqui a gente vai usar. let's prove this. So yeah, what's needed to here is basically some. Probably there are several ways to do that, but the cleanest way to do it is probably via a coupling argument. So what I'm going to do now is to consider this thing not as a conditional expectation, but as an expectation. Okay, and let's forget about this part because it disappears. Okay, when I take the difference. Okay, so now I will consider that I have two environments. Okay, I have omega and omega hat. Okay, and there are two. Okay, sure. Okay, and what's important here is that omega hat has the same distribution as omega. Okay, and you can consider that it's independent. Okay, and if you want, I'm looking at the space with like the product probability p hat. This is expectation with respect to omega hat. The thing that in everything we are going to do, actually omega is fixed. I'm just going to average with respect to omega hat. Okay, so now I'm going to define a new environment which I call omega n. Okay, and omega n kx, well, it's equal to omega kx if k is smaller or equal to n, and it's equal to omega hat kx if k is larger than n plus 1. Okay, so what I'm doing is I'm constructing an environment which is just distributed like omega, which is just omega until time n and omega hat starting from time n plus 1. Okay, and with this, okay, what can be checked is that mn, well, it's just the expectation of w and beta omega n. Sorry? Yes. Okay, when I'm taking conditional expectation, what I'm doing is I'm averaging with respect to things. Okay, so what I'm going to show is that w and omega n beta omega n divided by w n. Okay, so you have log and you have m n and well, okay, this thing. Okay, so let me rewrite this as w n n. Okay. So now this thing, it's equal to the expectation of the log of w n n plus 1 w n n. Okay, so what I'm going to show is just that this is smaller than 2 beta n. Okay, and I'll be done. Then I apply Azuma with k equal 2 beta m, and I get the result we wanted. Yes. Okay, and then yeah, no, we don't have the result we wanted. Okay, I wrote -2, and it's -1/8. Okay, because here the k² is at the bottom, so you get 2 times 2², which is 4. Okay, just missed a factor 16 somewhere. Okay. Okay, so why is this smaller than 2 beta m? Well, okay, here this is the sum of Gibbs weights. Here this is the sum of Gibbs weight. In these Gibbs weights, well, you have only, one term in the exponential that differs, and this term, the difference between the 2 terms you have, it's at most 2 beta m. Okay, so let's just write it. Okay, so. What you have is that Wn n plus 1 divided by Wn. And, well, it's the same as Zn n plus 1 divided by, okay. Yeah, no, it's not the same. Okay, it's not the same. No, it's okay. It's the same. It's, okay, because I'm just okay. So what you get here is the sum over x in omega n of exponential sum of n equal 1 to n beta omega n plus 1. Okay, here it's a k, I guess, k xk. And here you get the same sum. Okay, so now you get that this ratio here, okay, this ratio here, it's equal to exponential beta omega k xk minus omega k xk, okay, which is somewhere between exponential minus 2 beta m, exponential 2 beta m. Okay, so the ratio of each terms lives in this interval. So after summing, you also get something which is in this interval. Okay, and you get the concentration result we wanted. The z, it's a non-renormalized partition function. Okay, but doesn't matter. Like I don't have the, yeah, I didn't want to write the lambda beta here. That's all.
But shouldn't they be different for?
No, because the important parameter is n, and it's the same there. So you're always renormalizing by the expectation of Zn here.
Okay.
Yeah. I also got confused. So.
That's multiplication.
So what's multiplication?
The second equality. No. It's Wn equals N times the ratio of the sums. Or it's just.
No, sorry. I'm not sure I get it.
Okay, never mind. Wn equals N.
Well, here you know the Wn n, it's just Zn n divided by 2d to the n exponential n lambda n, lambda beta. So these things disappear. Okay. All good? So yes, what's next? Okay, so yeah, so now let me tell you finally about the very strong disorder regime. Okay, so this become a new. So you have f beta, which is the limit when n goes to infinity of 1 over n log wn. Okay, and if f beta, so you know that f beta is non-negative, and if f beta is negative, then Wn goes to 0, well, exponentially fast. Okay? I mean, basically, Wn, it's equal to exponential n f beta plus little o of n, okay, just by definition. Okay, so in particular, W infinity is equal to 0. Okay, so okay, so we see that very strong disorder holds when this free energy is negative. Okay, and very strong disorder implies strong disorder. Okay, okay, what you can also show, okay, and I will just do that now, is that well, you have a phase transition for associated with very strong disorder. Okay, so what's okay? Let's call it a lemma. What you have is that beta is non-increasing. Okay, so if you have strong disorder somewhere, then for larger betas you also have strong. If you have very strong disorder somewhere, then for larger betas you have very strong disorder. Okay, and the proof here, well, is simply that. Yeah, beta omega, I don't know. It's simply that, well, f beta is defined as a limit of non-increasing functions. And this is non-increasing, okay, for two reasons. Okay? I mean, this is because log is a concave. Okay. Log Wn beta omega is a concave function of zeta beta xn, where zeta beta is equal to exponential beta omega xn minus lambda beta. Okay, and we have seen that this family of variable is increasing for the convex domination order. Okay, so for this reason, okay, it's a concave function of each of these variables individually. Okay, and the other thing is that we have already seen, okay, also using FKG, that if you take the expectation of a concave function of the partition function, okay, then it's non-increasing in beta. I mean, you just compute the derivative, and at some point you use FKG to show that this is not positive. Or FKG for d beta. Log Wn. Okay, so this gives you the following picture. Okay. So, okay, let's say that D is larger than 3. Okay. And so we are going to see in a moment, okay, that F is not identically 0 if you assume something on the distribution. So, but yeah, you have some. Okay, so beta bar C, okay, it's just the max of beta such that F beta is equal to 0. Okay, or if you prefer the soup. Okay, also, okay, yeah, let's get it out of the way. Also, it's continuous, okay, simply because this function here, it's Lipschitz in beta. Okay, here I'm using bounded environment. Not needed again, but it's just convenient. Okay, and yes, so here I know that I have very strong disorder. And we have defined also another critical value of beta here, which is such that below here you have weak disorder. And here you have strong disorder. Okay, so a priori, with just the monotonicity results we have, yeah, you cannot say that these two things are the same. And it's a bit frustrating because the very good localization result that you can obtain them with this assumption that you have very strong disorder. Okay, so this is what we are going to discuss in the next lectures. Okay. Yeah, the fortunate thing is that now, okay, so this is not something I'm going to discuss in this class, but so this is from 24. And what you have is that beta C is equal to beta C for every d larger than 3, okay, and yeah, you don't even need bounded environment, and if you issue the result for non-bounded environment, it's on the archive since Monday, okay? Very, 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 very recent result. Okay, so yeah, so this result in particular, I mean, this result is in fact says more than this. It says whenever you have weak disorder, whenever you have strong disorder, you have very strong disorder. Okay, so in particular, it tells you that at the critical point, at the critical point, you cannot have very strong disorder because of continuity. Okay, so you know that f beta bar c is equal to 0. Okay, so since whenever you have strong disorder, you have very strong disorder, at the critical point, you cannot have strong disorder. So at the critical point, you have weak disorder. Okay, so this is somehow a small consequence of this theorem. Okay, so yeah, this we are not going to prove, but okay, perhaps something you want to know is that we are going to prove results about what happens in a very strong disorder phase. Perhaps you want to know that this is not empty, okay, so that indeed f beta is negative for beta large. Okay, so let's do this. Okay, and of course, I'm going to need an assumption, you know, because if you remember, yes, there are some cases where the beta 2, you know, that when the beta 2 was equal to infinity. Okay, so it's possible with some environment distribution that Wn beta is actually bounded in L2 for all betas. Okay, so proposition if the probability that omega 1, 0 is equal to essential supremum of omega 1, 0 is sufficiently small, okay, then f beta is smaller than 0 for beta large. Okay, sufficiently small. I will tell you what I mean by that. But the thing we are going to get is not optimal, so it's not very important to remember what it is. Okay, so in particular, if your environment is unbounded, this is true. If your environment has a density, this is true. Okay. Basically, if your environment is Bernoulli with some bias towards the soup, then this will not be true. Okay, so let's show this. So, okay, so the expectation of a log is not something very nice. So what we are going to do is to estimate something else. So, okay, an easy way to get rid of the log is to use Jensen. But if you do this, you get a bound which is 0, so it's not very good for our purpose. But you can do something a bit smarter. So, okay, you're trying to bound this. And then you can say, OK, perhaps I can work it a little bit before using Jensen. So I'm just saying that this is equal to this. Okay, I put square root here, and then I use Jensen. Okay, so we need to show that the expectation of square root of Wn decays exponentially. Okay, to prove very strong disorder, it is sufficient to show that this decays exponentially. Okay, and now, so square root is not really important. you can take Wn to the power theta for any theta between 0 and 1. And actually, if you optimize over theta, well, you get something better in terms of this bound. But again, this will never be optimal, so perhaps you shouldn't bother too much about it. OK. So what shall we do? Yes. Wn, it's equal to 1 over 2d to the n, sum over x in omega n, exponential sum from n equal 1 to n, beta omega n xn minus lambda beta. Okay, and now I'm using this subadditivity property for the square root. Okay, so you know that square root of the sum is smaller than the sum of the square roots. Okay, so. Okay, and again, this is true for any theta power. So. Okay, and then, yeah, the good thing is that now you can compute everything. Like, this expectation is computable. So what you get is that the expectation of square root of Wn, well, okay, it's smaller than, okay, now the expectation of this, it's the same for each term of the sum. Okay, so I get a factor 2d to the power n divided by square root of 2d to the power n. So I get square root of 2d to the power n. And then I get the expectation. Okay, I can tell you what I have. Okay, I have exponential n. Okay, here I have the product of n independent terms, and each term gives me lambda beta over 2 minus lambda beta over 2. Okay, so somehow, okay, here it's a bound, but this is reminiscent of the second moment computation, okay, except that you have things in the other direction. So if you remember that, you know that, okay, so this is equal to square root of 2d times expectation lambda beta over 2 minus lambda beta over 2 to the power n. Okay, so if I prove that for beta sufficiently large, this is smaller than 1, then I'm done. Okay, so let's do this. So what should I do? So, okay, if you consider the limit when beta goes to infinity of exponential lambda beta over 2 minus lambda beta over 2, well, this is explicit. This is the square root of the probability that omega 1, 0 is equal to its essential supreme. Okay, this is. I mean, okay. If you remember before, we have proved that the limit when beta goes to infinity of exponential lambda 2 beta minus 2 lambda beta is equal to 1 over this probability. Well, these two things are the same result. Okay, so basically, so is it the result? Yes. Okay, so if I'm not mistaken, this is what you get here. I'm a bit, okay. Okay. Yeah, I'm a bit surprised that you get something that good, but okay. Okay, so now let me tell you what we are going to do next, and this will be work for Friday, I guess, because this is quite independent of what we have done now. So yes, so there is, so I think we have shown that there is a very strong disorder regime. Okay. Also, like that this very strong disorder regime is in fact everything that happens outside of the weak disorder phase. So yeah, next thing we would like to prove is something about the polymer behavior in this very strong disorder regime. And okay, so let me tell you what the result is, and let me try to explain why this result holds. Okay. Yes.
Can you say a square root there? Because if you look at limit, it's going to be like some slight converged to one instead of decay system.
Okay. So where you have no square root? Sorry. Well, for me, like okay, here there is a square root because okay, let's say that this is equal to 0. Okay, so this Laplace transform converges to exactly this probability, and this one converges to 1 over the square root of this probability.
But my team is about the expectation of the square root of WM.
Yes.
In the limit, this guy is going to be bounded by 1, but not necessarily that the convergence is exponential.
What's okay?
You have that your expectation of square root of WM
is less than something which is smaller than 1 to the power n. Sorry?
Why is less than 1?
Why is this strictly smaller than 1?
Yeah.
Okay, because it's strictly smaller than 1 for beta large enough, because when beta goes to infinity, it converges to something which is smaller than 1, and it's continuous. So here, well, okay. If our probability is smaller than 2D, then the limit of square root 2D exponential lambda beta over 2 minus lambda beta over 2 is smaller than 1, limit when beta goes to infinity. Okay, so hence this is smaller than 1 for beta large. Okay, and when this is smaller than 1, here you have exponential decay in n. Okay, beta is a fixed parameter, you want exponential decay in n. Okay, so the idea is that, by using subadditivity, you're losing an exponential factor, okay? But you can get this exponential factor back. But for this, you really need beta large, okay? Because when beta is small, this goes to 1, and this is, okay, so if you need to prove very strong disorder for small beta, this will not help you. And this is, yes?
On the models that the physicists look, the distribution of omega will have.
They don't really care about the distribution of omega.
Okay.
Yeah, no, because I mean the history of this model is a bit like this model. It was first introduced as a toy model to study interface in some other two-dimensional statistical mechanics model. Okay, so it's already a simplification of a model. Okay, basically the idea is this model is not to do simulation. It's really to have qualitative results, okay, to understand what disorder does to the model. What physicists believe, and they are right about this, is that you have a general property of universality. If you don't mess too much with your model, like if you have an interesting model, basically, important results should not really care so much about the details of your model. Okay, so for instance, if you prove something with some assumption, then okay, it's still interesting to try to relax these assumptions because you want to make sure that you're not using, I mean, like your result is not dependent of the assumptions you've taken. But yeah, most of the time, things will be true when this assumption is not satisfied, provided that you're in the right class of environment. And yeah, and talking about physicists, for them they don't even need to prove things, so they don't really need to make assumptions on the environment. Okay, so what was I saying? Yes, about yeah, localization properties under a very strong disorder. Are there any more questions? Okay, so what are we going to prove? Okay, remember mu n. Okay. Okay, so this is not exactly the one that is going to appear in the proof. So I will define mu n. Okay, it's p n mu n x. It's p n beta omega x n equal x. So it's the endpoint distribution. Actually, what we are going to look at is, if you want, u mu n x, which is Pn minus 1 beta omega xn equal x. Okay, so it's not exactly the endpoint distribution. It's the endpoint distribution, but you don't put it, you don't put environment in the last step. Okay, so really our result is something about the sequence mu n infinity. Okay, so just the max over x of mu n of x. Okay, and well, mu n infinity, it's really comparable to mu n minus 1 without assumption on the environment. And if your environment is bounded, these two things differ by at most a constant, okay? But if your environment is not bounded, yeah, you have that mu tilde and mu n minus 1, they kind of look the same, okay? Because what you're doing is you're just taking mu n minus 1 and you're convoluting it with one step of the random walk. Okay. Okay, so the result. Okay, and this is not the result you find there. It's somehow a corollary of what you have there, and it's. But I think it might be more instructive. So the proof is that if you have a very strong disorder, okay, if f beta is negative, then almost surely the lim inf when n goes to infinity of the sum from n equal 1 to n mu n infinity over n is positive. Okay, so in particular, okay, this means that there exists delta positive such that positive fraction of mu n infinity. Okay, there is an n here. Is larger than delta. Okay, so okay, do you have stronger results than these? Yes. But can you prove that this is true? Okay, first, is this true without Cesaro taking this mean? No. Okay. Like the limit of this will be equal to 0 almost surely, and this is true for any beta at any environment distribution. This is basically because of a Borel-Cantelli argument. Okay, with some chance, basically the environment will be maxed on a block. Okay, and this is where your endpoint distribution will live, and here it is kind of a constant environment. Okay, so this will be very spread out. Okay, and by Borel-Cantelli, you will see infinitely many of these blocks. Okay, so then you can say, okay, yeah, but perhaps mu n converges in distribution to something, and this something has no atom at 0. Okay, and this is reasonable. This should be true, but people don't know how to prove this. What people know how to prove is that, yeah, if you take okay, this thing is a probability measure. Okay, and well, somehow it's not a very nice probability measure. So somehow, what people have done is they looked at this as an object which is kind of a probability measure, but modulo translation. Okay, and somehow with another twist, which is in the topology that you consider, basically, it's not, okay, they consider a larger space where you can have several measures with finite mass, okay, and the sum of the mass is smaller than 1. Okay, so you have several measures on ZD. Each of them you consider them modular translation, and the total mass can be equal to 1. And the idea is, yeah, you want to say something that if you have a Dirac at 0 and a Dirac at n, and you make n tend to infinity, okay, so this is a probability, okay, and when n goes to infinity, you want this to converge to 2 copies of a Dirac at 0. Okay, so basically, if you have 2 islands and they move far away, okay, then it converges in that space to. Okay, so this gives you like the topological structure of this, and basically, yes, if you consider this thing in that space, then it converges in distribution to something, and I don't see any reason why it shouldn't be true without this, but the proof uses completely, the proof completely breaks down if you don't use Cesaro means. Okay, so still lots of open questions there. Okay. Okay, but this is relatively simple to prove, and it already tells you, okay. Well, it already brings you a contrast, okay, with what happened in the weak disorder phase. Because in the weak disorder phase, you remember the last corollary I told you was that this thing goes to 0 almost surely. Okay, so yeah, the last comment I should do is to tell you, okay, why is this true? Why is this thing relevant here? Okay, so for this, you have to look really at what's Wn. Okay, what the increments of Wn are. So if you look at Wn plus 1 over Wn and the log, okay, because log Wn, it's really the sum from n equal 0 to n minus 1 of this thing. Well, okay, perhaps I want to write this like this. Okay. And yeah, this thing, okay, you can rewrite it as the log of mu n, okay, the sum over x, mu n minus 1 x, exponential beta omega x n minus lambda beta. Okay, this is just because this thing here, okay, I mean, it's just E n minus 1 beta omega exponential beta omega n xn minus lambda beta. Okay, I'm just writing the ratio. This I can write it as a, okay, I have Wn here. Here on top, I have basically the same density plus this extra term. So this is really the expectation. Okay, and this can be written as that. Okay. So if I have very strong disorder, okay, I can just look at this. Okay. So here imagine that all the mu tilde n are small. Imagine that this is small. Okay, so if this is small, this satisfies an approximate law of large number. Okay, so this should be 1, because this is the sum of small weights times independent variables that have mean 1. Okay, so basically, if this is small, Jensen inequality is close to be an equality, okay, when I take the expectation. And therefore, I get a contradiction to very strong disorder. So for this to be small, significantly smaller than 1, and this has to happen a positive fraction of the time, okay, I need here this mu tilde to be not spread out. Okay, and yeah, we are just going to put that on the rigorous round next time. Okay, so this is I think this will be the program for Friday, and afterwards we will prove that this beta bar c here is equal to 0 in dimension 1 and in dimension 2. Okay. Any question?